Lesson 18. Here it is, lesson 18. I kind of went over a little bit of this in the previous lesson, but this is lesson 18 is really interesting. I had some really cool videos to show you about what happens to charged particles when they get caught in magnetic fields. Well, charged particles from space, they get caught in the Earth's magnetic field, and since the Earth's magnetic field is strongest at the poles, the North Pole and the South Pole, we get what's called the northern lights and the southern lights. And what happens is those charged particles, they get caught in the magnetic field, and once they get into the magnetic field, they spiral. Or they form circular paths. And as they go in these circular paths, they give off electromagnetic radiation in different colors. And so that's why we see the greens and the blues and all kinds of crazy colors in the northern skies of the world and the southern skies of the world. That's charged particles getting caught in the magnetic field and giving off electromagnetic radiation, which is the next unit. So that's the beginning of this. Now, I already kind of discussed this part here. Right, a charged particle, let's just go over it again quickly. Charged particle electron goes into a magnetic field. This magnetic field is going into the board. And as a result, there's a force on the charged particle. If you use the third hand rule, your thumb is pointing to the right, your fingers are pointing into the board, and it gets deflected down. But since that magnetic field is quite extensive, it's a big magnetic field, it ends up, once it gets to this point here, once it gets to this point here, it's now going down. And so you have to change your hand rule. So now your thumb points down. And anyway, long and short of it, it ends up going in a circular path. And anything that's going in a circular path is by definition accelerating. Just remember that from physics 20. So if it's going in a circular path, then the magnetic force, here's the key of this lesson, the magnetic force must equal the centripetal force. And the magnetic force, when we're dealing with charged particles not in a wire, we deal with this formula here, QVB, the centripetal force from physics 20, mv squared over r. And so we can have, with a whole bunch of scenarios we can do, figuring out what's the velocity of a charged particle in a magnetic field, or what's the radius that it's going to go through. If we have an electron, we know the mass, it's going at this velocity in this magnetic field. What will be the radius of its of curvature of its path? So example number one, an electron moving towards a magnetic field at this speed, determine the radius of the electron's path if it enters perpendicular to the magnetic field. So that's exactly what we just did. The magnetic force must equal the centripetal force, QVB equals mv squared over r. And we're trying to find the radius. Solve for the radius, cross multiply, and then divide. So the radius is going to equal m. This will cancel out this. So it's going to equal, let's go to that, mv over qb. Okay, pretty good on that. Let's just move the r. Move the r up here. Oh, I want that red. Move the r up there, and then the q and the b are going to go down there, and this v over here is going to cancel that one. So there's your formula. Plug in the numbers. Well, actually, we'll go through it. It's an electron, so the mass of an electron is 9.11 times 10 to the negative 31. The velocity is given to you. The charge of an electron is 0.6 times 10 to the negative 19. And B is given to you. Plug them all in, and you end up getting an answer of 1.2 times 10 to the negative 8 meters. So that's the radius of an electron going through this magnetic field at that speed. Okay, moving on. Sometimes the magnetic force is balanced by gravitational forces. So in this case, what do we have? We have an alpha particle shot into this magnetic field at 90 degrees, so they're perpendicular, so it's the maximum amount of magnetic force. The magnetic force acting on the alpha particle is acting upwards. Determine the speed at which it must be traveling so that the magnetic forces balances out the gravitational force, pulling it down so the particle travels in a straight line. So you've got an alpha particle, right hand, that's being deflected up. So it's being deflected up, and we want to know at what speed. So the slower it goes, the less that force is going to be. If we slow it to a certain speed, it won't be deflected up anymore because gravity will be pulling it down at the same force that it's being pushed up, and therefore it will go in a straight line. So you see this question again, the alpha particle, if you just go really fast, it's just going to go whoosh, it's going to go up because the magnetic force will be so strong. But if we can slow it down, eventually the magnetic force will start to decrease because of this formula here, Fm equals qvb. Right? If we decrease the velocity, then Fm gets smaller. If we decrease it enough, we'll get to the point where the magnetic force pushing it up is equal to the gravitational force pulling it down, and therefore it will just move in a straight line. So this is Fm equals Fg. Fm qvb. Fg mg, and we're trying to solve for the velocity. Velocity equals mg over q b. Plug the numbers in, pretty straightforward, and you end up getting this answer. 0.42 meters per second, which is very slow for an alpha particle moving at that velocity. Is very, very slow. Okay, example 3. So these examples, I know some of them will translate to the assignment that you're working on. Hopefully it'll make sense. Example number 3, we got an electric balance by having a length of current carrying wires sitting in a magnetic field. If no mass is on the scale, the wire will be in equilibrium position. When the mass is placed on the scale, the wire will be pushed down. A certain amount of current is needed to force the wire back up to its equilibrium position. A particular electric balance has a length of wire. So in this, let's write down the variables we have for this one, because this is a little more complicated. We have the length of the wire, 0.289 meters. Placed perpendicular inside this magnetic field, B is 3.75 times 10 to the negative 3 Teslas. If the current, current is measured in amperes, A, but its variable is I, 7.81 times 10 to the negative 2 amperes, is required to balance the scale after an object is placed on it, determine the mass of the object. So what do we have here? Once again, like the previous question, we have the magnetic force is going to be equal to the gravitational force. But in this question, since we're given B, I, and L, we're going to use this formula here. You remember this from the previous unit, or the previous lesson rather, equals B, I, L, and then add a sine theta on there. But since it's perpendicular, then it's the maximum amount of force, so it's just BIL, you don't need sine theta, equals mg. And in this one, we're determining the mass. The mass equals BIL over G. Plug your numbers in, pretty straightforward, and you end up getting 8.90 times 10 to the negative 6 kilograms. Okay. The next concept, I'll just go over this quickly. It's not you're not going to be tested on this. You might if you're writing a diploma, but it's really interesting. The magnetic force, and there's some really good videos on this. You should Google the magnetic force on 2 wires and watch some videos of what happens to the wires. Because if you have 2 wires side by side and you run currents through them, then they're going to produce a magnetic field around them, and of course those magnetic fields will interact with one another, and the wires will actually be forced together, or they will be pushed apart, and it's a very noticeable phenomenon. So here's how that works. So if you have the current running in the same direction, here we have the current running here's your 2 wires, and they're both running into the board. And therefore the magnetic field is counterclockwise in both of them. Counterclockwise. Now, what we've done here is we've put a little magnet here and here, and labeled them north and south, because the magnetic field always goes away from the north into the south. And same for this one here, into the south, away from the north. And since the we have here a north-south and here a south-north, you can see that these wires will actually attract one another. So if you run the current in the same direction, then they will attract each other. If you run them in opposite directions, if you run the current, so in this example, the current, this one's going into the board or into the page, this one's going out of the page. If you run them in opposite directions, then those wires will repel each other. Okay? And again, please go and Google this, watch a video on it. Very pronounced. Okay, so I think that, yep, that's lesson 18. Lesson 18 is done. Lesson 19, you should read over it. We're not going to do too much on it because I want to do lesson 20 and 21. Once you've done those ones, that's magnetism done with, and we can move on to electromagnetic radiation. So I'll be back in a second to do lesson 20 and 21. Hope you're getting this. Stop recording. There it is. Bye-bye.